let's move to the next talk. Our next speaker is Dr. William Payne. He's going to be the founder and CEO of ScaleOut Software. So that he and his team is building a very customized MapReduce engine only for the real-time analytics. Before ScaleOut Software, he has founded 3 startups. One of his solution was the web load balancing solution we did acquired by Microsoft. And now he's using the Windows Server machine as network load balancing solution. Apart from being himself a serial entrepreneur, he's also helping many of the startup companies in Seattle as a venture capitalist. So please welcome Mr. Payne.
Very big difference. So well, thank you very much for inviting me, and we very much appreciate it. I was sitting there and I thought of something that I'm probably the only person here who can say that they've been using my Yahoo as their homepage for 17 years without interruption. Maybe someone else can say that. Okay. So anyway, I'm going to talk to you today about real-time analytics for online systems. And so that's a very broad topic, and there are many areas like the work in complex event processing. We're going to talk about how in-memory data grids can be used to accelerate real-time analytics and use Hadoop MapReduce to run that analytics for some very interesting applications that our companies run into. So first, I'm going to give you a very quick review of what an in-memory data grid is. How many of you are familiar with Oracle coherence or gigaspaces or grid-beam? Everybody knows about that technology? Yeah? All right, well, I'll do a quick review. And I'll tell you about some of the needs that we've seen for real-time analytics, and then how in-memory data grids can be applied to that problem. I'll tell you about a method of data parallel computation that we use to implement Hadoop MapReduce. We call it parallel method invocation. And I'll give you some sample use cases and show you a little video if time permits. So, moving right along. This is the only slide about our company, but it's obligatory I have to put out there. So, we've been in business for about 10 years in the market since 2005. We have 400 customers. We're typically a closed source software company, but we do have a hybrid open source product with this Hadoop offering of ours. So that's why, I know if you're used to open source technology, it's a much bigger number of customers than 400, but they're all paying customers and running on about 9,000 servers. These are some of our customers there. So what we do is develop in-memory storage technology and use it to scale computation and to scale in-memory data storage. And I mentioned a while ago that I came out of Microsoft, and I first saw this problem when I was at Microsoft, when everybody was putting data in SQL Server to share across a big server farm application or a web server farm. So in-memory data grids really started coming to market in about 2002 with coherence from Tangosolve, and we introduced our product in 2005. An in-memory data grid is interesting from the previous talk. Absolutely, SQL is great, but in-memory data grids are designed to fit in the business logic layer. They're not the same as MongoDB or Cassandra. They're not long-term persistent storage. They're more ephemeral storage for fast-changing data. And the key is the data is changing quite rapidly on a millisecond or less basis. So you need a business logic view of the data, an object-oriented view, and typically they fit into either Java or C# as collections of objects which can be accessed directly through APIs, create, read, update, delete, people call that CRUD, and also by query based on properties. And so those are some of the key ways that in-memory data grids have been used in historically before real-time analytics. Now they're implemented across a cluster of servers or a cluster of VMs, and the grid's job is to spread the objects out with a load balancing technique across the servers and implement high availability through data replication. And we have quorum-based access to the data, so it's reliable updating in the presence of server or network failures. And so what you want to get with any kind of technology like this is what was first identified by a guy named John Gustafson at Los Alamos many years ago, also Cleve Muller, the guy who created MATLAB. It's called scalable speed up. And it means as you increase the workload, you increase the number of servers, and hopefully you see a linear increase in throughput. And that's the prime way that we measure the performance of our grid. Now what we've seen is a need for real-time analytics, which is a relatively small part of the overall spectrum of analytics. Most of the work, as we all know here, has been done in batch mode for static offline data sets, typically very large, petabytes, exabytes, and looking for long-term trends, data mining that may take minutes to perform, sometimes hours. In In real-time analytics, of course, you want to get answers much faster. In real-time, it's different things to different people. We're not talking about a flight simulator. We're talking about applications in e-commerce and also in financial services. So we're talking about getting results in milliseconds to seconds instead of minutes. And that's the spectrum of real-time that we can apply in-memory data grids to. And so it's primarily used for tracking live data and for identifying patterns and trends that can be acted on immediately. Here are some examples that we have seen in the market for the need for this type of real-time analytics. And you might be wondering, how does this compare to Storm? How does it compare to Spark? How does it compare to CEP? And so we don't have time to talk about all that. But the prime answer is that we're focused on fast-changing data, online systems where the data is changing on a millisecond by millisecond basis, and yet you still want to do a Hadoop MapReduce on that data to look for patterns and trends. And what's key is that the flow of data coming through the system is a small part of the overall population of data, and yet you're doing the MapReduce on a very large data set, relatively speaking, might be in the gigabytes, hundreds of gigabytes to terabytes. So as opposed to CEP, which is looking at that stream of data, so you're looking at a much larger data set that's being influenced by the incoming flow. Also, you want to be able to use MapReduce to not only analyze the data, but to update it in real time. And that's a second big benefit you get by integrating Hadoop MapReduce with an in-memory data grid. So here are some applications in financial services, and I'll show you the little videos of a hedge fund managing trades using real-time analytics with this approach, data parallel approach. Also e-commerce, logistics, I'll give you an example of that. Also for choosing, helping customers choose products wisely. Credit card fraud detection, airline reservation systems, many applications, military and otherwise, so telecommunications. So lots of need for this kind of technology. And so we believe that the way to harness MapReduce, and we think MapReduce is a very powerful, it's a simple, relatively simple, well-understood model. The key thing is well-understood, large population of users. And if that can be sped up so that we can get answers in milliseconds to seconds, there's a real benefit to the community that's storing this fast-changing memory-based data. And the way we approach this, and we think is a viable way to do it, and we spent the last year developing it, is to integrate a Hadoop MapReduce engine, not using it off the shelf on the Apache one, for example, but to develop one from the ground up and integrate it directly with the grid. And we do that using an underlying data parallel computation technique, which I'll tell you about. And our product is called ScaleOut H server. I'm going to say H server. That's what I'm referring to. So I want to this is a slide I put up for a talk in New York about a year ago, because I'm a relatively old person compared to you, and I've actually seen most of those machines. I just wanted to give you some perspective that that data parallel computation goes back decades before MapReduce. In fact, I think one of the earliest real contributions was Danny Hillis's thinking machine called Connection Machine 5, and that was what's a single instruction, multiple data, fully custom hardware implementation. And people realized, and my boss at Intel, I worked at Intel for 11 years, Justin Ratner, who brought data parallel computing and parallel computing to Intel, created a series of parallel supercomputers that were also created at IBM and InCube and other companies. And their approaches used commodity processors and then used custom networks. And so they were using cut-through routing and techniques that were not available in commodity networks, and still you wouldn't find them because switches, and as we saw in the last talk, networking was getting so fast, and you had InfiniBand with RDMA. So in any case, people that moved on to clustering, right, because now you don't have a custom network, let's have all commodity hardware, and so the software techniques were evolving as well from having single instruction multiple data to single program multiple data, and using message passing, so that MPI, message passing library, and HPC became very popular. And then we see MapReduce being deployed starting, I looked it up, I think 2003, correct me if that's wrong, was when it emerged. And on clusters and in the cloud. And now we're talking about applying MapReduce to in-memory data grids hosted on clusters and in the cloud. So the technique that we deployed on our in-memory data grid, which I haven't seen in other products or open source, and let me just step back. You sometimes think of this technology as being the same as Memcache. Memcache is a cache, so therefore it always relies on a backing store, and that's different than an in-memory data grid. An in-memory data grid is it's a store of reference. It's a store it's the authoritative store for the data that's changing typically between transactions in an e-commerce system or over the course of a trading day in a financial services system. It does not have its data backed by secondary storage. So therefore, the techniques you use, such as data replication and dynamic load balancing, you won't find in Memcache, just for those of you who wonder how it's different than Memcache. In any case, we put this technique we call it parallel method invocation, but it really is a very standard approach to data parallel computation that has emerged with the MPI library back in the 90s. And what happens here, what we've done is put an object-oriented spin on it because the data in the grid is object-oriented. We're storing instances of Java objects or C# objects, as I said, referenced either directly with key values or through parallel query. But in addition, you can do data parallel analysis on those objects using parallel query to select the object that you want to analyze, and then applying a method, equivalent to a map method, we call it val or analyze on that data, that picture from, and then doing what in MapReduce is called combining, which is what we call merging. And the difference is that we do merging that goes not just within a server, but across all the servers, so you get one result, a global merge across all the servers. And one of the things we learned in parallel supercomputing is that if you can do that in logarithmic time, you're doing really well. And so we've implemented binary merge trees with binary combining to do that in logarithmic time. And then we use this as the underlying engine to build MapReduce. First, let me tell you a little bit more about PMI and how it works. The first step is a parallel query specified by the user, and that is applied to all the servers. It generates a pool of objects. So you wouldn't do this in Hadoop MapReduce, but you would do this with PMI. And the next step then is on every grid server, the selected objects are then put through the equivalent of the mapper multi-core execution engine, which is going to produce results which are then combined down to one object. And then in the final step, all of the combined objects are merged together. Now this is not MapReduce, but it doesn't. But it's not a subset either. It's sort of a dialect, because it does this global merging. But we use this to build MapReduce, and I'll show you how on the next slide. But anyway, this is a technique that we can deploy with very simple APIs. And I just want to, this is not in this column, it's a backup slide, but I think it's useful to see it. So this is an example in Java. You would just implement an interface that we call invocable that provides two methods, right? Think of them as map and combine, very simple. Except that you can pass parameters to it, which is very valuable for real-time analytics, because if you have market data flowing in, for example, you need to be able to pass live market data to the mappers if you will distribute that market. And then, next slide shows you. So this is the invocation. You select a namespace in the grid, and then you simply, with one line of code, specify the invocation, this parallel method invocation. And notice you get back the result on that one line of code. So it's very, very simple. That's the point I wanted to make by showing you that. We ran this, just to give you an idea of the scale, we ran it on Amazon on 75 servers. We did a terabyte data set. This is before they had the large memory they have now. They only had 60 gigabytes per server at that time. And we wanted to demonstrate that you could have a large in-memory data set. This is a terabyte. I realize for you MapReduce people that's infinitely small. And then we wanted to churn that data at a fairly rapid rate. So we churned it at 1.1 gigabytes per second. This represented financial market data updating stock history objects. Each object there was a history of some stock, like AT&T, for example. And then we were running a risk analysis called backtesting. And we wanted to see how long it would take. So we were able to do that at the rate of 250 gigabytes per second. That is to say, we could analyze that whole terabyte in 4 seconds. And then what's interesting is if you look at those lines here, first of all, it shows linear speed up. That's the Gustafson's law being applied to analytics. As you increase the problem size, you increase the number of servers. I've seen some companies in this space not apply that, take a fixed problem size and add servers, looking at a graph like that. But the thing that Cleve Muller and others first identified in the mid-'80s is clustered systems need to have the problem size grow as you add servers to ameliorate the overheads of especially the communications. And so the way you really harness the power of clustering is by scaling the problem size. And you want to have linear speed up. So anyway, and you see that can actually double the throughput of analytics if you don't turn the data. Essentially, by turning the data, you're slowing down the analytics because it can't client-side cache all of the data in the grid. Okay, so now the next part is to tell you how do we implement MapReduce using this underlying parallel method invocation, or PMI. I'll call it PMI for now. And the goal here, of course, is to be able to sit on your workstation and do a MapReduce and then have the code sit out just as you would with normal MapReduce, right? And then get your results back. Hopefully, maybe not. Maybe the results don't have to be stored in the grid. They can be returned directly to the workstation. And that's something that PMI can deliver as an extension to MapReduce. I won't be talking about that now, but we actually make use of that. So we use pure Hadoop MapReduce, but then we have the ability to do final combining across all of the servers and return the final results if that's what we do. So one thing I want to point out here is that part of our PMI implementation is to build what's called an invocation grid, a set of JVMs or .NET runtimes. Our products run for both Windows and for Java, Linux. We try to make everything have parity, although we have not implemented these APIs in C# yet. So the idea here is that when you invoke a MapReduce, started a MapReduce job, we're going to spin up the JVMs, but we also give you a hook so that you can keep those JVMs and then run, and you can do continuous MapReduce on the same set of JVMs. We call it an invocation grid. And that's a very nice feature, which you'll see how it helps reduce the startup time dramatically. So what we do to implement this, it sort of falls out very naturally. You do two PMIs. The first PMI is to spin up the mappers. And you can take it, because this is its own MapReduce engine, but it's source code compatible with Hadoop MapReduce, so you can use any input format you want, in particular HDFS. And HDFS can decide about the splits. Or if you use the grid, then we automatically decide about the splits. So we can do a lot of auto-tuning, by the way, by using the grid as the source and also the sink, if you will, for the output data. And you don't have to then explicitly manage splits and partitions. So the PMI runs, and that binary merge I talked about is what notifies us that we've completed the mappers. And we push the data. One of the constraints of this implementation is we're pushing all the intermediate data into the grid. We're not pushing it to local disk or to any other secondary storage. So we can only do problems for which the intermediate data will fit in the grid. For online real-time, it turns out that's fine. For some problems where you're going to take a petabyte data set and create a lot of intermediate data, it wouldn't be fine. For word count, that's fine, by the way. We did a benchmark with word count just to show how it would speed up relative to the Apache version. So then we do a lot of optimizations to push the data, to do a lot of combining. We do very aggressive combining, and we push the data into the grid. Our goal is to minimize data motion, eliminate it from secondary storage, and minimize it across the servers. So there's algorithms that we use to carefully stage the data in the grid. So when the reducer startup as a second PMI, of course it's only going to be pulling local data, not data across the network. Although, as you probably know, in-memory data grids can transparently access data from any server. But we want to avoid doing that for performance reasons. And then finally, the reducers run and the output flows out. So one other point I want to make is that you can optionally turn off sorting if you want to. It just fell out of the implementation, and we don't use sorting in most of the algorithms we deal with. So this just shows you that it can be accomplished with one-line function as well as C#. But all we did was subclass the job object, so there's that one line down there. It's called H-server job now. So it's a very simple code change to use this custom engine. How are we doing? Okay? About 5 more minutes. Okay. So also you can access data from the grid, and we've added our own input formats and record readers, and say on the output side, so that it's a very optimized approach to moving data into the mappers or out from the reducers with a lot of pipelining to and from the grid. Also, something we observed is in-memory data grids have been around for a decade or more, but they actually, their objects tend to be very heavyweight because they have a lot of semantics like pessimistic blocking. In our case, we have accessibility from remote stores and other locations. We have dependency relationships, just a lot of metadata. And we found, if you want to implement word count and store that with typical objects, it wouldn't work. It's just too memory intensive. So instead, we implemented Java concurrent map, we call it AMAP. And it's very, very efficient with memory, but it has much more limited semantics. But it's very, very fast. And that's really necessary. So I just, one of the things we did with run word count, we were able to get a 20x speed up. I realized, 20x doesn't sound like very much when you hear Spark say 40 to 100, right? But 20x is actually a pretty big speed up compared to the Apache. So these are two examples, and then you'll see how this would get you. This is a customer we have in Southern California dealing with perishable goods. And the problem they have is that they have an ordering system and an inventory system, and they're siloed from each other. And they have to reconcile that. And they typically are doing it at 2 in the morning offline by doing queries, SQL queries, pulling a whole bunch of data out of their database, trying to find a way to schedule it in parallel and get some speed up. It was taking 2 hours to run. It's just a monster. And so we suggested they use an interim data grid. And the key design decision we made when doing this, or any form of data parallel computation I've seen, is what is the domain on which you do the mapping, right? And so in this case, it turns out not intuitively, it's the SKUs. And so in real time, you use CRUD operations to add data to the SKUs based on the orders that have come in and the inventory changes. And then you can run as a Hadoop MapReduce a reconcile, which is their secret sauce about how to do very efficient reconciling for their system. And so they do that, and then just spit out alerts if there's something unusual. But typically, the reconciled data goes right back in. So this is pure analytics. Now, this is a case where you're doing updates in analytics. This is a hedge fund, and the domain here are the set of hedging strategies. So I don't know if you know much about hedge funds, I do. But a hedge fund looks at a bunch of market sectors and keeps long positions and short positions to hedge their holdings. And so what we would put here in each hedge strategy object, for example, automotive, transportation, retail, whatever, is a set of positions which we would update through a market feed. Now in this case, we can use MapReduce to update these strategy objects and detect whether there was an imbalance and whether a trade needs to be made and to send out alerts. So this is a case of using MapReduce, which I think is fairly unusual, to not only analyze data but to update it in real time. So I'll just show you this video hopefully. So I'll just walk you through this real quick. So this is the trader's display. We just mocked this up for this hedge fund. And on the left-hand side are the strategies. They normally have names, we just gave them numbers. And so there's 2,000 in this case, and there are 2,000 strategies and 40,000 positions. So each strategy has, as you can see, ticker symbols representing the long and short position for a hedge, they're called. And then you can see the market prices are dynamically being updated by MapReduce right there. We showed this at Strata a couple weeks ago. And then what happens is we're trying to, when we update them, we check the allocations to see if they deviate a certain percentage. And if they have, then we trigger an alert. Now this shows you, we're doing MapReduce operations in about 350 milliseconds, very fast. And it backs off and shows you that's the Apache MapReduce below. And that's, as you can see, it takes about 15 seconds. So that's the benefit. So they were actually taking 15 minutes to do it, and they're thrilled to be able to do it under a second now. As you can imagine, in a market trading situation, the closer to real time, the closer you could disrupt the markets with automatic trading. The more effective your trading system will become. Okay, so we have that. So we've got a couple more slides and I'm done. Okay, so just one, there we go, comparison to Spark. I didn't have time to talk about other things like Storm and CEP, but Spark. So Spark is actually really close, and I get the question a lot, why are we just doing Spark? And the reason is because Spark, to my understanding, from my reading, and I'm sure there are experts here that know a lot more than I do, is really designed to harness in-memory computing to accelerate MapReduce and extend it to other operators, but it's not really designed for online, fast-changing data that has to be instantly available. And so therefore, the implementation is different. There's a benefit when you say, well, I don't care about online. I think Spark will run faster than this, and I'm pretty sure that any kind of a bake-off, they will win. But on the other hand, we have to maintain the data at all times. We can't reconstruct the RD, resilient distributed data set. We have to have that data set live at all times. So that's one of the differences, is that it's working on live data, and so the availability model has to be different for the data. The other thing is extensibility. And as you know, as we all know, the Spark has operators that go beyond MapReduce, and that's really terrific. We can implement such operators. We haven't yet, but they can be implemented with PMI, because if you remember, the PMI underlies this, and you can do anything you want in a PMI method. So, for example, you can implement filtering with a PMI, or any of the other operators that are available in Spark. So they both have extensibility mechanisms. So let me just wrap up by saying we've been focused on online real-time systems and showing how in-memory storage and in-memory computing, in particular as manifested with in-memory data grids, is a very effective way to plug into an operational system and hold fast-changing data and analyze it in real time, and by that I mean milliseconds to seconds. And we looked at how we implemented parallel method invocation as a fundamental part of our grid, and then built Hadoop MapReduce on top of it so that we could bridge the MapReduce community to this technology and be able to use MapReduce to solve some of these problems that our customers have. So thank you very much. Are there any questions?
Thank you, Bill. Nice talk. I have the question is you have analyzed the stock data. What kind of degree, how deep you analyze? Like say you with like a moving average or like the orange band or any deeper analysis, something or just daily high, low, that kind of thing.
Well, so I talked about two different algorithms. I assume you all heard the question. So two different financial services algorithms. One is back testing. And actually, we have a white paper on the back testing algorithm. We're not experts in financial services, so we used a company in New York called Lab 49, and they are experts. They used about 8 different algorithms for back testing. And I don't remember them. They're very complex. You need to be in computational finance to understand them. But what we did was we had a contractor build a back testing library for us. For the hedge fund itself specified the algorithm they wanted, and so we just dropped that in for how they wanted to look at the long and short positions and decide whether to alert a trader. So that's really not something that we have expertise in, but it's something that shows that the platform is very extensible, can be used for a variety of different things. By the way, this platform could be used to accelerate Hadoop and also Hive, and those are things we're looking at now for query and other things. It's just a matter of the problem is how do you plug in, to the open source code bases to do that. But there are a variety of ways we can build on top of it. Also, machine learning that we're seeing from some of these emerging companies, and I'm trying to think of the name, I can't remember the name of the company I saw last week. These are things we can build on top of this platform. Is there anything else?
A quick question. So in the first use case you mentioned, the size of historical data is 1 terabyte. I would like to know what is the size of your live data and what kind of analytics you were conducting for real-time analytics. The size of live data as well as what kind of operation you are conducting for real-time analytics, also live data.
So this is a simulation of a backtesting system. So what we did was we generated market price changes at a rate of 1.1 gigabytes per second, randomly spread across all of the equities that were being stored in the grid. And then each of those objects in the grid held a history of stock prices. And so we're adding a new price and deleting the old price. And then we're just continuously running the backtesting algorithm I just described on that. So what we're trying to show here is that you can churn a subset of the data in the grid at a high rate, 1.1 gigabytes per second, and still do MapReduce very, very quickly in just 4 seconds across a terabyte of data.
I understand that's just a simulation, but I would like to know, if you don't mind, tell me what is the size of your live data. Historical data is 1 terabyte. What is 1%? Or 0.1%, tell me how large is the size of data, live data?
Well, remember, it's a stream. We have a thread running on each of the servers that's doing an update to each of the objects randomly picking a stock. So I guess we can compute that. I don't know the exact number, but 1.1 gigabytes per second of data is changing. Okay, so that's the amount of data that's changing of that terabyte. So thousands of that total data set is changing every second. Okay? So 1 gigabyte is the size of the change every second. I hope that answers your